So just a reminder, the last 2 weeks we'll have our the last 2 quizzes. All right. So go to your tutorial section. So for both courses, we're going to have the last 2 quizzes in the last 2 weeks. Quiz number 2 for 248 will be on double integral. Quiz number 2 for 246 will be on solving the second order differential equations. Okay. So take it as a sort of a warm-up for the final exams. So there's only 2 weeks left for the lectures. Okay, so let's continue on the 248. So in previous lecture, we started on the topic of vector field. And we talked about a similar concept called line integral, but this time it's a vector line integral. So you do a line integral in a vector field. Okay. So now the question here is, number 1, if you recall that the line integral basically C f dot dr, right? That's the line integral. So the question is, okay, can we avoid doing this line integral? So essentially, if under what situation that we don't need to carry out this integration at here, basically, all right? Yeah. So that sort of give you a shortcut. So here's the situation here. Now this f here is the vector field, right? It's a vector field. Under certain situation, the f, where's f from? So but sometimes your f, if you recall that, can be from here. So what's over here is basically you have a scalar function f, and you take the gradient of the scalar function f, then you got a gradient vector, right? So that gives you basically a vector field. So this is a special case here. Okay. So we'll see that when your vector field f here is actually coming out of here, and basically f is result of a gradient of a certain scalar function, okay, then we don't need to carry out this integral anymore. We have a different ways of evaluating this vector line integral here. Okay, yeah. So this one here is a what we call a special kind of a vector field. Okay, so we'll see why this is special though, right? Yeah. Now, in general, okay, this f here, so it could be a function 2 variable, or it could be a function of 3 variable, or even more, right? Okay, so for this f here, there's a name here. We call what we call it. Okay, it's called potential function. Okay, this is called potential function for f vector. So potential, this is actually not a new word, right? We know what potential. We have potential energy, we have a gravitational potential, we have electrical potential, right? So basically, this is what this general wording at here referring to those specific cases, right? Yeah. So for example, we have an electric potential. Okay. So electric potential is a scalar. Okay. Okay. Electric potential is a scalar function. I'll show you what it is. Electric potential is a scalar function. Then when you take the gradient of this electric potential, you get your electric field. Okay, so the electric potential is a scalar function, and its gradient, okay, gives electric field. All right. Yeah. So since the other example is you can have a gravitational potential. And its gradients will give you the gravitational field, right? Yeah. So as a matter of fact, if you recall this del F, basically it's a gradient, right? And what does it point into? It points into the greatest increase, the direction of the greatest increase of the function F, right? Yeah. So there are different ways of illustrating that, but the one way of illustrating that is to use either level curve or either using level surfaces, right? So those level surfaces and level curves is like potentials, basically from one potential to the next one there, and the direction, which is the gradient of that function f, gives you the greatest increase. Okay, if you have a negative here, it's basically greatest decrease, right? Okay. So let's see a quick example here. So let's say if I have an electric potential here, basically, so we'll use a charge for illustration. All right. So maybe I have a charge right here, okay, with a Q, and here's a point in the space. Okay. The position is indicated by a vector r, or the distance here is r. And as you learned, or your third year you will learn it again, the electric potential the electric potential, we use phi e at here, okay, is basically Q over 4 pi epsilon naught and R. Okay, so that's electric potential. Okay. So epsilon naught is a constant, okay, electric constant. Okay. Then if I take the gradient of this one here, okay, if I take gradient of this, yeah, then I will get the electric field. Or more precisely, there should be a negative in front here. Okay, I will get the electric field. So taking the gradient of this one here is nothing really tricky. All you need to do is Q, and this is our constant. The only variable here is R, and R is the distance from there to there. So R is x squared plus y squared plus z squared. So what happens is you're gonna just basically taking partial derivative of this one over x, partial derivative of this one over y, and partial that over z, right? And you calculate this thing here, you will get your electric field, which is basically Q over 4 pi epsilon naught 1 over r square and r hat. So the r hat is the direction pointing in that direction there, right? So okay, so that's basically the sort of example here, electric field. So similarly, you can also have here, similarly, for gravitational ones. So for gravitational one here, your potential, gravitational potential, okay, is V equal to negative G m over r. That's the gravitational potential. So G here is the gravitational constant, m here is the mass of the Earth, okay, and r is the distance. Okay. If you do the same thing, excuse me, then I can get a gravitational field G equal to negative del V, okay, and that'll give us negative G capital M over R square and r hat. Okay, so that's gravitational field. So gravitational field basically at the at the ground level, right? And you have this 9.81, right? And if it changes, then you have a different g value. As a matter of fact, there's this European satellite which is actually falling down already. And you're watching the news, right? So that satellite, there was a satellite that was falling off from the sky and doesn't know where it's gonna be. Actually, chances are going to be Canada. And that satellite was used to basically do a survey of this gravitational field around the Earth, right? At different locations, basically give you a map of this one. But that task has finished, so the satellite basically not being used and it's kind of being brought down to the Earth. So that's the relationship here. But in general, okay, just remember. So now when you look at this one here, this f here, not just a scalar function now. You can call this f as a potential function. Okay, yeah. Okay, so now here comes a very important theorem. Okay. This theorem is called fundamental theorem of calculus. Okay. Have you heard of this? Fundamental theorem of calculus, right? Well, not exactly this one here for line integral. Okay. So I guess, excuse me, when you're learning calculus in the first year, if we just say fundamental theorem of calculus, then what happens is, if you have an integral of f, okay, which equal to this antiderivative f here, right, then this a to b, let's see here, will basically is fb minus f of a. Okay, that's fundamental theorem of calculus here, right? Yeah. Now we have a similar theorem, okay, but this is for vector line integral. Okay, yeah. So here is the this is nothing to do with the theorem here. Okay, so here's the beginning of the theorem here. Given a curve C, okay. So let's say the curve C running from P0 to P1 point. Okay. And let's say if I indicated the C as using a parametric equation R of t, okay, then the t range from A to B. So which means basically at t equal to A, you are at the P0 point. At the t equal to B, you're at this P1 point. Okay. Yeah. Now if I have a vector field f, okay, which is the gradient of a scalar function f, okay, then the line integral, which is the one that we're trying to evaluate, okay, so we're evaluating the line integral over this curve C, okay, then as we said, we're not going to evaluate this line integral as we did in the previous lecture. Basically, you're putting all the parametric equations into it, right? Parameters. So what we do is, this theorem says is, you can evaluate, because now it's this f is this, so what happens is, okay, so we just replace the f with del f, and how you evaluate? You evaluate just based on the difference between these two values. Okay, yeah. So that's this fundamental theorem of calculus for line integral. Okay, this is a very important theorem. It's very simple, but it's very useful, though. Okay. So let's take a look at this writing here again, and then let me explain it again here. So you're evaluating this line integral. Right now, the current vector field is basically a gradient function f. Okay, so f is a potential function now. Then the value of this line integral basically is the difference between the value of the function f at the p1 minus the value of function f at the p0. Is that clear? Yeah. So let me give you a quick proof of this one here, okay? Yeah. So we have the C here. Let's say I'll write the C out as a general vector. And we know that T is from A to B. Okay? Yeah. Then when I'm evaluating this line integral, okay, since this f, okay, is a del f, and t goes from A to B, so my line integral can be written as this one, right? So I replace the f with del f, and this dr here, so let's say I write a dr over dt and dt. Okay, so that's the same thing. Okay, so this is basically the definition of a line integral now. Now let's calculate this del f here, right? Calculate del f. Well, I'm not sure what it is, but I'll just put down this general del f gradient of this one, basically fx, fy, and fz. That's the gradient vector. Then dot the derivative of this one here. Okay. So your parametric equation is this. So the derivative is dx over dt, dy over dt, and dz over dt, and then dt. Okay? Yeah. So here's the dot product. So just carry out the dot product using the definition. So what do we have here? We have fx dx over dt plus fy, okay, dy over dt plus fz dz over dt, okay, and dt, right? So dot product, just add them together. Okay. So now multiply the dt into the bracket. So you cancel all this dt over here, right? So you end up with fx, fy, dx, dy, fz, and dz. Okay, so you end up with this. Okay, so what exactly is this one here? Perfect gradient. And what do we call this again? Total what? Total differential, right? This is a total differential for the function f. So basically it's df at here, right? Total differential. So this one here equal to A to B df. Okay. Well, you're integrating. So this has happened again. So you integrate anything, d anything, you come back to this f here, right? So the result of this one here is f what? F at this t equal to b at t equal to b minus f at this t equal to a. Okay. So basically this is f x of t, y of t, and z of t, and when t goes from a to b. So when you substitute the t equal to b into these points here, that gives us the point p0. That gives us the point p1. When you sub the t equal to a into here, that gives us the point p0. So this is why the original theorem f p1 minus f p0. Okay? Yeah. So here's a short proof of this calculus, a fundamental theorem of calculus for line integral. Okay. So what happens here? When do you use this theorem? Basically, you can use it when this vector field f is the result of the gradient of the function f. Okay, that's when you can use it, right? Or later we'll call it, this is basically what we'll call f is a conservative field. Whenever f is a conservative field, you can use this theorem. Okay? Otherwise, you can always rely back to your original general way of solving line integrals. So let's take a look at an example here. Okay. So this example is an example I think in the tutorial. Basically, this line integral example here. So this is the in a tutorial example. You have a piece of pizza, okay, or a loop inside this vector field, and now we're trying to calculate the line integral go over this closed loop here, okay, along the edges. Now, in the tutorial, what happens is you calculate it essentially. You calculate it separately, C1, C2, C3, by substituting the parametric equation, this general approach, right? Yeah. So now we're going to try to do is let's look at if we can use this fundamental theorem calculus to do this one here. Now, if you recall that this vector field, okay, is yx. Okay, this is the vector field f here. Now, for now, if just give you a vector field, it's very hard to say what exactly this vector field, right? But I can tell you this vector field is actually a result, a product of this gradient f, where f equal to xy, right? So we'll figure it out later. How do we find? How do we know whether this can be a result of a certain gradient of a certain function? Okay, but for now, if I say function f is xy, and you take gradient of this one here, and you're gonna get this vector field f here, right? Okay, yeah. So that's good. So that basically telling us the f, okay, is satisfying this one here. Then I can use my fundamental theorem calculus now, right? Yeah. And to use that, basically when you integrate from integrate over C1, C2, C3, you're gonna need the value. If you look at this fundamental theorem here, you're gonna need the value of this function f at the end point, and starting and end points of each segment of the curve. So the first step, you need to find the coordinates of each one of these end points at here, terminals. So the coordinates are actually quite easy. A is 0, 0. Okay. And B is going from here to here, so that's 1. So the B is 1, 0. Okay. Is it 1, 0? Yeah. C, I have a mistake in my lecture notes. So C is not C, D. So D point is over here. So this angle is 45 degrees, pi over 4. Okay. So this pi over 4, and this is part of the circle. The radius is 1. So you can easily calculate the coordinate D by 1 multiplied by cosine theta and then 1 sine theta, right? So that'll give you the D coordinates, which is 1 over root 2 and 1 over root 2. Okay. Yeah. So that's the three coordinates for the endpoints here. Now we know that our line integral, okay, over this total C here equal to C1, C2 plus C3. Okay, so that's the property of this sort of integrals applied to any cases. So what about the C1 now? So basically C1 is f dr, that's a C1, right? Okay. So I'm not gonna evaluate this one. I'm gonna evaluate using the fundamental theorem calculus. So according to this theorem, so what I have here is f, the scalar function f at the end point of this curve, which is b, minus the f value at this starting point a. Okay, right? So that's what it means here. So what is my f here? F is xy, right? F is xy. So now the question is fb basically is f what? f1, 0. Okay, f1, 0. And because f is xy, so you substitute this 1, 0 there, you get 0, right? You get 0. Is that clear? Yeah. And fa apparently it's f0, 0, so that's another 0. So then this whole thing is 0. Okay. So the first line integral is 0. And second line integral, okay, is f. The second one is c2, so this portion here. And so it started to be, it ends as a d. So then according to the fundamental theorem, it's f value at the d point minus f value at the b point. Okay. So we already have b, so we need f of d. So what's f of d now? D is 1 over root 2, 1 over root 2. Okay. So x, basically this value multiplied by this value, which is 1 over 2. Okay. And this line integral, so 1 over 2 minus 0, so that's equal 1 over 2. So that's the line integral of the second segment. The last segment, so last segment is from D to A. So your A is the end point, and your D is a starting point. Okay. Yeah. And A is already 0, and D is this, so negative 1 over 2. Okay? Yeah. So now you have all three segments, so add these together, apparently they're equal to 0, right? Equal to 0. Okay? Come again?
Is that because you're doing a loop?
Yes, exactly. This is because it's a loop. Yeah. So as a matter of fact, it doesn't really matter what kind of loop it here is. As long as you started here, then you come back, your line integral will be 0 for this case here. This is actually the next point. So this is basically the question here is you have you have this special kind of a field, which is f equal to this, right? You have this special kind of field. Now this special, actually we haven't really seen why it's special yet, because we have a name for this one here. This when f equal to del f here, so we call this f, okay, is called conservative field. Okay, it's conservative field. So conservative, it's a word that I think we have come across so many times from high school here. Conservation of energy, right? Conservation of energy here, basically. Okay, so when you have a conservative field, then the following thing will happen. Okay, number one thing is path independence. Okay, so path independence. So that's the first thing that will happen. So you see the previous case, right? It's the previous I didn't show you the path independence yet, but where can we see the path independence? The path independence can be seen directly from this fundamental theorem of a calculus. So let's say, for example, right? I have if there are C1 and C2, okay, connecting. Okay, P1 and P2. So basically, this is P1, this is P2, this is C1, and this is C2, right? So you can go either way to get to P2 from P1. Okay. Then, when we have a conservative field, okay, we have a conservative field, and when we wanted to integrate this line integral there. Then according to the fundamental theorem of calculus, so one is C1, right? And the other is C2. But doesn't matter which one it is, as long as they have they share the same starting and end points. Your end result is f of P2 minus f of P1 according to this fundamental theorem calculus, right? So that's why it's path independent. Now, if we think back about this line integral, when we learn line integral, one example I think a practical example I showed you is consider you have a force field and you have a curve C, and then you're trying to move a mass around this curve C, right? So eventually we're going to be interested in what is the total work that has been done by the force field when the mass is moving from one point to the other, right? Yeah. So a very simple example, this is gravitational field. You lift the mass from here to there, right, by a height of h. So really doesn't matter where you lift it. You lift this way or that way, right? As long as the same height h there, the same amount of work is done. Okay, so that's basically path independence. So path independence exists in many cases. You're learning thermodynamics. The first law of thermodynamics, there is this work, right, done by the system. And that basically is also path independence. Okay? Yeah. So this is important to the theorem basically because why? Because when you're given a question, okay, when you're given a question asking, okay, here's a vector field, here's a curve C, calculate this line integral. Okay? Yeah. So if you directly jumping into it, you may find it very difficult to calculate. But if you see back, you find out, oh look, my vector field is actually equal to del f coming from a gradient function f, right? So then you say, okay, I don't really need to calculate this line integral anymore. I can just simply evaluate this line integral by looking at the difference between the end and starting point of the function f value. Okay, yeah.
I'm just confused. Like, when do I know that I can use that fundamental theorem?
Yeah. When do you know that? When you know that f equal to this. We'll explain how you know that, but that's basically the number one. You know your f coming out of this vector field, coming out of the gradient of a scalar function f. Okay, that's when you can use this fundamental theorem calculus. Okay. Of course, the million-dollar question is how do I know, right? So that's where we're going to cover next. Okay, but doesn't matter. The number one thing is if you know your vector field is a product of taking gradient of a scalar function f, and basically you know the small f there, the function f, then you can use this theorem here. Okay, yeah. Okay, so the next thing is when you have a conservative field, first thing is path independence. The next thing is when you have a conservative field and basically your line integral over a closed curve is 0. Okay, that's the next thing here. Okay. As a matter of fact, yeah. This is actually one of this one here. Basically, when you have this condition, this is essentially necessary or sufficient condition. So if and only basically you can also derive based from this condition saying that f is conservative. Okay? Yeah. So when you have a conservative field and you're giving a closed loop curve C, so forget it. The line integral must be 0, right? Don't even bother to calculate. Okay. So I might give you a question like this, which is very challenging in terms of calculation. So if you spend 1 hour trying to calculate that, then you're deadly wrong. So this basically the testing point here is, right, the fundamental theorem of calculus. Okay. So now I can summarize up just a little bit here before we move on here. Some of the important facts here. So we have 4 equivalent properties. Okay. So what are the 4 equivalent properties? Number 1. Okay. So number 1 saying that f is conservative. Okay, this is one property. So when we say f1 is conservative, first thing jumped in mind is this closed loop. Okay, again, line integral should be 0. Okay, that's one. Second of all, okay, when this conservative, okay, and it has this line dependence, path independence property. Okay. And third of all, okay, when you see that f is conservative, then you should know that f, okay, must be from, okay, del f. The only question is, so we need to find out what the f is, right? Okay. So in such case here, we call this f is a gradient field. Okay, gradient field. And the last one is a sort of property of based on this one here. So let's see if f, okay, is a vector field M in P. Okay, so certain vector field M in P. Okay. And because, and this small f here is a certain kind of scalar. Because f is conservative, then I know that this capital F vector equal to del f. So when I equate this, okay, when I equate this equal to this, so what we're going to get, basically we're going to get we're going to get this m, so dx plus n dy plus p dz, okay, equal to fx dx plus fy dy plus fz dz, which is a total differential. So this is basically from the line integral here, okay? So when you substitute f over here, okay, and replace the f with del f over here, okay, so you're going to end up with this one here, okay? That kind of we kind of show this one in the when we're trying to prove the fundamental theorem in calculus, okay? Yeah. So basically, you can conclude that this m equal to this, and n equal to that, and p equal to this. Okay, so that's the property of this. So those four are basically equivalent. You mention each one of them, you're talking about the other three. All right, so that's the nature of these things here. So if I just say f is conservative, I'm actually meaning all of the other properties there. All right. Yeah. Okay. So any questions? No good. So now let's go into the next one here. Basically, is number one question is, how do we know that f is conservative? And how do we find, right? First question, how do we know f is conservative? How do we find that if f is conservative, how do we find an associated scalar function f such that del f equal to this gradient field? Okay, so that's the two things we need to figure out. Okay, so number one question, okay, is, okay, how to determine, okay, how to check, okay, if a given, okay, f is conservative. Okay. Yeah. Okay. So here's what you do. Basically, here comes another theorem. Okay. Here's another theorem. F is conservative. Okay. Very simple. If and only if. Okay. Okay. Del cross f equal to 0. Okay, so if and only if del cross f equal to 0. Okay, so this is actually one of the a new operator you're seeing in here. Now, in previous lecture we learned what the del is, right? So we learned del. Basically, we learned how to apply del to the f. So now, what is del? Del basically is an operator, right? It's an operator, and it's actually in a vector here. Basically, it's d over dx, d over dy, and d over dz. Okay, that's del. So now, this theorem says f is a conservative if and only if del cross f equal to 0. Basically, you use this vector cross the given vector field f, You want to see whether that's 0 or not. If it is 0, then it's conservative. So, in other words, the mathematical meaning basically saying, when you say f is conservative, that means this. If this is 0, that means it's conservative, right? So there's two sides here. Okay. So how do you prove this theorem? There are basically two parts. One part is to basically f is conservative. You can prove that, and when you have that, that meaning this is conservative. So I'm not going to prove this one here in the class. You can take a look at the lecture. You can take a look at the textbook for proof. For the proof, we actually need another theorem called Stokes theorem. That's what we're going to learn in the future, right? Yeah. But for the time being, this is actually very simple theorem to apply. F is conservative. Okay, if and only if the cross product of the two is 0. Right? So now let's calculate the cross product. Okay. So actually, right now we come across with a brand new things. Later we're going to call this is called a curl. Okay. So IJK. Okay, IJK. So it's the matrix, right? Second row is this one. Last row is vector f. So let's see, vector f is m and p. Okay, so three quantities, components. Okay, so this is f right here. Okay, and now you need to calculate this determinant of this product, the matrix. Okay. So that's actually a very simple cross product, and just be careful with the calculating. But eventually, you calculate this one, you're getting up with partial p over partial y minus partial n over partial z I hat plus partial m z and p y x. And partial n over x partial m y. Okay, so you will have you will end up with this results in here. Okay, so that's the result of this cross product. Yeah, some of you may think this is negative, but actually I already put a negative into the bracket, so that's positive there. Okay, yeah. So the theorem says f is conservative if and only if this cross product 0. So which means if I set this cross product 0, and I'm going to end up with basically what? 1, 2, 3 equations, right? Yeah. So I'm going to end up with basically 3 things. That means partial p over partial y equal to partial n over partial z, and partial m over partial z equal to partial p over partial x, and the last one, partial n over x equal partial m over y. Okay, so that's what we're going to end up here. So f is conservative basically means the 3 equality at here. The 3 equality at here basically means f is conservative. Okay, so that's basically logic at here. Okay, is that good? Yeah, so there's no trigger here. So now next we're going to learn a new concept here, but we'll just show you here. This del cross f here is called curl f. Okay, curl f. So operator, linear operator. So we were talking about linear operator. You know, a gradient is a linear operator. Now then this is a new operator here, the curl. Okay, so basically this del cross. Okay. This del cross is another operator. Okay, yeah. All right, so you can very easily verify this one here. You can prove, you can prove that del cross del f equal to 0. Okay. So why is that? According to theorem, so when you have a del f at here, when you have this del f, that has to give you a so-called what? A conservative field, right? And if it's a conservative field, according to the theorem, then the cross product of the conservative field is going to be 0, right? So del cross the gradient of anything is going to be 0. Okay? So you can very easily prove this one. Okay? Why? Because f equal to this is conservative. Okay? Yeah. Okay, so now we know how to check conservative. Now let's take a look at an example here. Okay. So I'll give you a vector field. Okay. So here's a vector field. First, is this a conservative field, right? So okay. So how do we check? We have this theorem right there, and so let's check this whether f is a conservative field. So number one, I guess let's put down the corresponding components correspond to that theorem. This one has only two components, so this is a 2D vector fields. So basically, this is your m, and this is your n that are here, right? And the p term equal to 0. Okay. Yeah. So now if I'm going to apply this theorem, so let's say basically what I'm going to do is I'm going to check this del cross f, okay, whether that's going to be 0 or not. Okay, so this is what we're going to check. So according to the formula, let's take a look at the formula here. This is a del cross f. This is what they here, right? So now the p is 0. So now p is 0. So this is gone here, right? P is 0. And the other thing is this is a 2D plane. So 2D plane, the function m and n, they're not going to be function of what? Z. So eventually, this term, they're gone, right? They're gone. So you only have this last one here, okay? Yeah. So now let's take a look at what it is. Yeah. So del cross f, okay, and basically in this particular case, just partial n over x minus partial m over y and k hat. Okay, so that's what this one here, 2D, right? That's basically applied to any 2D situations. But you also need to be careful though, huh? Basically, you could have a situation that here's a function x, y, z, but there's no key component, right? You could have a situation that, right? But in that particular case, then this is not true anymore, okay? So go back to the original formula. Okay. So let's say what is dn over dm? The d partial n over x. So this is n here, right? This is n. So partial n over x. Yeah, I'll give you an exercise here. So what's the partial derivative? Let's try it out. So yeah, you do it and calculate and see if you get the same results as what I have here. So it should be pretty quick, right? Is that what you get? So you get 0, right? So you get basically you got a 0 here. Yeah. So which means the vector field F is a conservative field. Okay. Yeah. So check. All right. So now the question here is, okay, if this F is a conservative field now, and then according to the property, right? According to the full property here, when F is a conservative, then F must be a product, a rule, must be a result of the gradient of a certain scalar function. So what would be that scalar function f then, right? So that's basically the next question here. So f is conservative. And this means f equal to del f. Then my question here is, what will be this scalar function f? Okay, so let's find it out here. F equal to what? Well, f equal to what? It depends on the vector fields, right? So now let's say, suppose that I kind of know what f is, but I don't know. But let's just use this use this formula here. Okay. Right now, my vector field is mn. Okay, so it's this 2D vector field, and that equal to this del f. So del f is fx, fy. Okay. So which means this m would equal this fx, this n would be this fy, right? Yeah. So what's my m and n? M and n, we know that m and n is, this is m, this is n and here. Okay. So basically from this one here I would get partial f over partial x equal to the m, and m is 6xy squared minus y cubed. And the other condition is this partial f over partial y equal the other one. That's what? N, right? 6x squared y minus 3xy squared. Okay. So this is our starting point. Okay. We're trying to find the scalar function f. And the function, small function f, has to satisfy these two conditions. Right? Has to satisfy this condition. So now let's look at how do we find f at here. So you can start with each one of the conditions here. All right, you can start with any one of these. So let's start based on this first one here. So this is where we're going to start from here. Okay, yeah, we're going to make use of all of this here, but we'll start from here. Now we started from here. Now what happens is, you know, the ideal situation, if I tell you this, oh look, df over dx equal to x squared. Okay, if this is the case here, so what would you do to get f? Integral, right? You're going to integrate. The only thing is, that's good. So maybe I'm going to basically integrate both sides of this one here, right? But the only thing is here is, this is a partial derivative. You have y here, but that's okay, right? When you take a partial derivative over x, what did you do with the y? You consider y as a constant, right? So we're still going to do this. Basically, we're going to integrate. So we're going to integrate this both sides here. So integrate. So integrate both sides. But you need to know that when you integrate this both sides here, you're integrating with respect to x, okay, not y. So when you're integrating with respect to the x, then you're considering the y as a constant there. Is that good? So here's what happens here. So when you integrate, basically you move this dx to the other side. Then when you integrate this left side here, you get what? You get back to this function f, right? Yeah. So you end up with your original function f at here. Is that clear? And the other side is you're just integrating this 6xy squared minus y cubed and dx. Okay, dx. So that's where you're integrating. Now, but here's one thing here. Let me put down this simple one case here. Okay, yeah. For when you're integrating a single variable function, when you're taking derivative of a single variable function, and then I said, okay, let's calculate the f. So what would you do is you have a df equal to x squared dx, right? Then you integrate both sides. Okay, so then you end up with this f equal to this 1/3 x cubed. But don't forget what? Plus constant c, right? Okay. So similar here. So if I have this, if I'm going to integrate both sides of this one here, and I have this function f coming out now, and I have an integration of this one here. So what should I do? I should also plus a c So now the big question is should I plus just a c now? Well, you plus a c at here because this is a single variable. But now what happens at here is you're integrating with respect to the x, you're considering the y as a constant, right? So instead of actually plus just a constant c, you actually plus a what? So instead of, I call it c here, I would call it using r here. A function of y. Okay? So here's how it works, right? Here's how it works here. So the derivative of this one give you back this x squared. And when it's constant c here, the derivative of constant c is 0, so it's gone. Make sense, right? And same idea. The derivative of this one with respect to the x should give you back this one. Right? That's called antiderivative concept. And if this is just a function of y, then the derivative function y with respect to the x is always 0. Okay? Is that okay? Okay. Any questions on this part here? Yeah.
You get so many solutions.
Oh yes, you can get so many, but in this case you will just have to choose one solution. Yeah. But for now, I don't know what this is yet. But for now, all I know is I need a function of y at here, right? But you cannot just get rid of this one, right? Okay? Yeah. Is that clear? Okay, so now calculate this integral. This is a very simple integral. Just integrating with respect to x and consider the y as a constant, right? So you end up with a 3 x squared y squared minus x y cubed plus r y. Okay. All right. So if you always remember, you can always check, right? So everything goes with logic. You can always check. So checking means, okay, so here's f of x, y. How about the partial f over x? Will you get back to the 6x squared, 6y squared minus y cubed, right? If you take a partial derivative of this, you get back this. Okay? Yeah. Okay, so now the question here is, now what will be this r, y? So the function, this r here. Well, I guess now we're going to have to resort to the next condition. Okay, the next condition here. Okay. So how do I apply the next condition then? So apply, okay, next condition. Okay, next condition says partial f over partial y equal to this one, right? Equal to this. So I haven't got exactly what the f is there, but I got this f, which is this one now, right? So what I'm going to do is we'll just take partial f over y. So basically take this partial, this function of this partial of this function over variable y. Okay. So let's say partial f over y. What does that give us? And the first one is y. There's a y, and then there's another y, right? So the first one gives me 6x squared y minus 3xy square, okay, and then the partial, well, the partial is not partial anymore, just derivative. So that's just r prime y. Okay. So that's partial f over partial y. And what does that equal to? The next condition. That equal to this guy, right? That equal to this guy. And so that's basically, let's let it equal to 6x squared y minus 3xy squared, right? This is basically, which quantity is that? That's m, right? That's n, sorry. That's n there, right? That's n. Okay. So you have this equal to this. So coincident, not really coincident, but in this case here, you check the both sides. What happens? What? Here, 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 here. They're gone, right? They're gone here. So all you're left with is r prime y equal to 0. Okay, so r prime y equal to 0. So derivative function r with respect to the y, so this is basically dr over dy equal to 0. If dr equal to 0, what does r? What's r? What does what does r give us here? Constant, right? Okay. Okay, that wakes you all of you up. So r is basically a constant. Okay. If r is a constant, so I'm going to put it back over here. Okay, so that equal to sorry. So if you're watching the video later, you probably get startled. Okay, so this is 3x squared y squared minus x plus c at here. So that's fxy here. Now, so back to sorry, what's your name again? Cosine, yeah, cosine question. So you have an infinite solution set here, right? But you don't really need the infinite solution. You only need one. So if I only need one, which one should I pick? I guess I'll pick the easy one. So I'll just set a c at here equal to 0, right? So basically we're going to just have to pick fxy equal to 3x squared y squared minus xy cubed. Okay? So if you want to pick a +1 or 2, that's fine. So always double check, right? And double check basically means take a gradient of this function f and see if you could get back to the vector field f. Okay? Yeah. Is that good? Yeah. And if you have this case is a 2D vectors, right? These are 2D vectors. Now if you have a 3D vector, okay, so then it will be p term, and the chances are you're going to have to go over 3 steps. So first step to apply the first condition, second condition, the third condition, right? So it'll be relatively more more computation, but the idea is the same thing. Okay. Yeah. The key idea is this one here. Okay, is this one. The key idea is first step when you integrate both sides. Okay, first step when you can integrate both sides, you shouldn't just add a constant c. So if if this is just a function of 2 variables, you add a function of y. So let's see what happens if this is function of 3 variables. You have x, y, z at here, and at the first step you're integrating both sides. So instead of a function y here, so that will be a function what? YZ, exactly. Okay, yeah. So that's basically the key point. All right. Good. Any questions? Yeah.
I didn't understand the second condition. Applying the second condition.
The second condition, yeah. So the condition here basically is based on this theorem, right? Because this is conservative, then we know that f must be from the gradient of certain scalar function. And based on this equality here, we know f already, okay? We know f. Based on this equality here, and then we have this m equal to the partial f over x, the n equal to partial f over y. So this is basically the 2 conditions I was talking about here. Okay? So your scalar function f has to satisfy these 2 conditions. If it's a function of if it's a vector, 3D vector, then it'll be the third condition, right? And then the process is you can start from each one of this one here. Doesn't matter. So I started with this first condition. Based on the first condition, I end up with this function f, which is this one here, with the unknown function y at here. At the same time, you know this f has to satisfy the second condition. Satisfying second condition basically means partial derivative of this results, preliminary results, should satisfy the second condition. So this is why we take a partial derivative of f with y over here by retaining this r of y as it is. And we get this partial derivative, right? And this partial derivative satisfies the second condition is basically equal to this right side here. This is right side. So then you cancel this one, you get this one equal to this 0, and then r equal to c. Okay? Yeah. Good. All right, so that basically concludes this conservative field. Yeah. Any questions? Okay. Okay. Okay, so now let's continue on the topic a little bit here. To start the topic, so the topic here is a curl. Okay. and its application, of course. And then, but mostly, okay, we're talking about its interpretation. Okay. So I guess I mentioned the curl when I was talking about the conservative, checking conservative. So I said curl basically is a del cross f, right? I said del cross f. Then you kind of know already. Well, okay, so what's the curl? Curl is del cross f. And then how do I calculate the curl? Here is what the formula, right? Here's the formula. So if it just from the calculation point of view, it's very simple. Okay, nothing else at all. But the only thing is, let's talk about the interpretation here and how's that formula from? Where is that formula from, basically? All right? Yeah. Now let's start from a simple sort of analogy here. So let's say I have a spring at here. Okay. So you have a spring. So the spring was spitting out this water, right? So if you consider the spring as a skitter source, so basically you can consider this spring here. This is skitter. Okay, the skitter, right, spit of water, it generates a vector field. Okay, generate vector. So a skitter generates a vector field now. Okay. So then the next question here, if I have a vector field now, so basically you have a magnitude of and direction at different locations of the vector field, right? Okay. So the next question is, will a vector field generate another vector field? Okay. So that's basically sort of a preliminary question here. So will a vector field, okay, produce, okay, another field, vector field. So this is more of a still a kind of like an input-output type of question. Say for example, right? You have a vector function f, and if you consider this an input, you give it to the operator del. Del you consider as a system. Then what does it yield? It yields a vector field, right? Yield a vector field. Okay. So then if I give this vector field to something else, then will it generate another vector field? And well, I guess the answer is yes, right? It's very simple. Of course you will. Now let's take another example here. Suppose that I have a river, okay, and I'm going to model the river using a vector field of this one here. Okay, so I'm going to model the river using V equal to this. So if I draw this vector field out, okay, so this is x-axis, this is y-axis, and you will have a vector field more like this one. So this is 0 point. At the 0 point, okay, along this 0 point, it has the longest, basically, a magnitude of vector. And as it going along, okay, to the other two directions, the vector, okay, getting smaller, smaller, okay, like this. Okay, like this. So this is actually basically, if you watch a river, that's how sort of all it goes. The river runs faster in the middle, but it's sort of slowing down along the two banks, right? Yeah. So now, if I toss a stick into the river, maybe I'll put it over here, and maybe I'll put it over here, right? So what would you expect the stick to do? Rotate and, well, the river is flowing, right? So it's not going to rotate, but also it's going to moving forward, right? So basically, the stick will have a translational motion and rotational motion. Okay, but use your intuitive. If I put it on the top here, and how it's going to rotate? Which direction? Clockwise or counterclockwise? Counterclockwise. So this one here will be clockwise, right? So basically, what happens to here is this is a vector field. Now you put something into the vector field, and then there's a rotational behavior due to this vector field. Okay, so there's this rotational behavior. Okay, so this rotational behavior is actually basically the motivated the finding of this so-called curl of a vector. So this basically motivated finding this so-called curl of a vector field. Okay, so that's the motivation in here. Okay, now talking about this curl, and I have to go back slightly go back to this to the line integral again. Okay, so let's go back to the line integral here, and then we'll talk about the concept called circulation density. So going back to line integral, vector line integral. Okay. Now, when we talk about line integral, here's the line integral f, okay, and d and s and here c, okay. So over a curve c, okay, over curve c. Particularly, one of the line integral that we were talking about is a line integral over a closed curve c. Okay, closed curve c. So when we have an integral with a circle here, so that basically this is the line integral over a closed curve c. Now, for this particular case, this is called circulation, right? If you recall that, circulation. Circulation basically means it's a line integral, okay, over a closed curve C. Okay, that's a circulation. So you're talking about how much of this vector field will circulate around a closed curve C. Okay. Yeah. So as we just learned today, if f is a conservative field, then it's going to be 0, right? Yeah. Now, circulation basically it's a sort of a concept here. Let's see if I think about the circulation like this. Okay. So I have a vector fields, right? I have vector fields. Okay. And C is some kind of a closed curve. So let's use a simple case here. Maybe C is like this. Okay, maybe C is like so. Basically, C is a closed curve and parallel to this xy axis, right? However, if I keep the C, basically still keep the same circle, But if I tilt it a little bit, if I maybe tilt it a little bit like this, right? Yeah. So basically same circle, but it's being tilted. I guess when you try to calculate circulation around this one or around this one, they're going to be what? Different, right? They're going to be different. So even if the C enclosing the same amount of area here, all right? So basically, the idea what I'm trying to say here is circulation has this concept of the orientation. So when you orient this curve C differently, you'll get a different circulation. Is that okay? Yeah. So this is a sort of a, also you can think of this. Let's say I have a pinwheel, right? And if you hold your pinwheel at the different angles, and it'll basically rotate at a different speed, right? Yeah. So that's the sort of the concept of orientation in it here. Okay. Now, so orientation matters. Okay. Orientation matters. So what else matters, right? What else matters? So here's the next thing that we're interested. When you're integrating over curve C, maybe the curve C is big, this much big, maybe it's small, right? But it doesn't matter. When you're integrating over the curve C, you're basically considering along this whole curve C here. However, in certain situation, what you're interested is maybe you're not going to just interested in just circulation over this much of area. Maybe you're only interested in a very locally area, just a dot, right? Just a dot here. For example, you want to use a certain device to measure the wind speed. So what do? You just hold it up and measure the wind speed, right? So basically, that's in terms of the wind speed vector field. That's pretty much a dot in the field. Is that right? Yeah. So the second basically here is maybe we're interested Okay. So we're interested in circulation, okay, around a very small area, or maybe just a point. Okay, or just a point. Okay. So in this particular case, this basically brings the concern of this basically brings to the next logic called circulation dentist. Dentist. Circulation density. Yeah, I guess maybe I was recalling my dentist appointment. So, right. So this basically brings this one called circulation density. Okay, circulation density. So now let's take a look at this concept, this circulation density, and yeah, we don't have much time, but I'll just draw the drawing here, and as to how we're going to look at this circulation density here. Okay, so this is how we're going to look at this one here. We have a vector field. I'm not going to draw the vector field anymore. Okay. Now, since we're looking at a very small area, or even just a dot, so what we're going to do is we're going to draw a very small area, okay, and basically using a curve, closed curve C. Okay, using a closed curve C. Okay, I'll just draw arbitrary curve C. Okay. For simplicity, consider a planar, basically planar region, okay, surrounded by this curve C. Okay. So here's a curve C now, and a couple of things we're going to define it here. Basically, it's the orientation of the curve C, and there's a region here. So what happens here now? There's a region, okay, enclosed by C. Okay, and we're going to consider basically a planar region, okay, not a irregular surface by the curve C. As a matter of fact, we're going to look at that later. And because this is the region here, and because the C can be oriented differently, then what we're going to do is we're going to basically use a normal vector n hat, okay, at here to represent this normal direction of that region. Okay, is that good? Yeah. Now here comes question here. There's always a compatibility between the direction of the curve C and the direction of n hat. And we're going to look at this later too, but you need to be basically for now, you know, the right-hand rule has to be satisfied for the direction of the curve C and direction of n hat. So for example, C direction is this, then the n hat will be your thumb direction. All right? Yeah. So the way I draw here satisfy right-hand rule. Okay, and the next thing here is for this particular region, and we're going to have define a so-called area vector. Okay, area vector. So usually when we talk about area is scalar. Now because the orientation, we have this area vector. So area vector, if this is delta A for this area at here, then delta A by n hat is the area vector. Is that good? Yeah. And when we learn surface integral, this is what we're actually going to use here. Okay? Yeah. So area vector. So this is a delta A vector here. Okay? So I'm going to stop here. So we're going to make use of the notation in here to sort of derive this curl formula.